Welcome back to our engineering mechanics lecture series, for which we are looking at everything related to forces so far. And particularly, we are still analyzing the equilibrium of particles in 2D systems, because in our next lecture we want to move on to 3D systems. But before we do that, we need to have a solid understanding of how these forces work, particularly the tensile forces, because only tensile forces act in cable structures. We talked about this a little bit last time, but today we're going to solidify that knowledge because it's so important when we move on to 3D systems. Because sometimes cable structures actually stretch a lot, we need to understand how to calculate that and how to determine the stretch in those systems. And that is often described idealistically by springs. And so one big goal of today's lecture is actually to look at springs. In fact, that's the only part that we're going to talk about theoretically, and the rest we do all in applications through solving problems. So very little theory today, only problem solving. So that at the end, which is our ultimate goal, we can calculate the tensile forces in more complex cable structures. That include springs, and then also we're going to use the educational opportunity to make our systems a little bit more advanced. So without further ado, let's move on to springs, and let's start talking about what is actually called linear elastic springs. So let's talk about those two terms real quick. So because we're only talking about linear elastic springs, so let's talk about linear before we talk about elastic. So linear in a sense means the more of something the more of something else, or sometimes less, the more of something else. So of something else. And of course, this could also be less here. And this is not completely true yet linear, but in a general concept, it is true. So if we apply, let's say, more force, we get more stretch. But linear doesn't just mean more and more. It also means that if you add twice more, you also get twice more of the other thing. So it's pretty much a linear function, if you will. So let's visualize that. So of course we remember this from our basic math class. What is linear? If we have a graph, and let's say on the graph here we put what engineers call delta, which is usually displacement. And then we put a force here. So we apply a force to a spring, and then I would apply, let's say, 1 Newton, and it stretches by, let's say, 1 meter. And then I apply 2 newtons, it stretches by 2 meters, and so on. So what we would end up with would be a linear line, right? So that would be linear. Now, that is the first term, and I will come back to that in just a second, although it's a very basic, probably already understood concept. But for completeness reason, let's also talk about elasticity, or what is elastic. So elastic means that you always go back to your original shape, right? So you stretch something, and when you let the force go, it goes back to state zero. So that means it is recovering deformation after force has been removed in case of springs. So let's draw these two aspects, linear and elastic, for actually springs. So let's say I have a ceiling, which is very long, so I can apply multiple springs to it. And let's say I have my very first spring here, and there's nothing on it. And I'm gonna call this length that the spring currently has, I'm gonna call that L nut. Right, so the initial length. So this is L nut. And now I'm gonna take the very same spring, but I will apply a force to it. And I will apply, let's say, 1 Newton to keep it easy for us here. And therefore my spring just became a little bit longer. And the way it got longer is really described by the difference from the initial length to the second length. So this would still be L nut, but this here is delta L. And I'm going to call this delta L1 because here I have, let's say, 1 Newton. Now, if I apply more force to the system, the stretch spring will be even longer. And so I end up with a system that is longer. And of course, I need my weight down here again. And let's call that 2 Newton. And to no surprise, I now have a different length. And that different length now is up here still L nut. And here I have delta L2. And just for completeness reasons, let's draw one more. Let's draw one that goes all the way down here. And now I have a box with, let's say, 3 Newton on it. And my stretch now, of course, is even longer. And I still have this L nut, but now I have delta L3. And in this case, delta L1 is equal to 1/2 delta L2, for example. Right? So this here is twice as much as this one because I have twice as much force hanging on it. And that's really what the linearity stands for. Likewise, let's say my delta L1 is also equal to 1/3 of delta L3. Or you might as well say it the other way around. You may say that delta L3 is equal to 3 times delta L1. And so you understand now that the linear elasticity means the more force you put on it, the more it stretches, and the stretch is proportional every time you add more to the system. And that is really what this picture here signifies for you. Now, again, if let's say you call these state 1, or this is called 0, this is 1, and then second and third state, and let's do a fourth state and maybe even a fifth state. So if I now remove the force again, and I will actually draw my initial line, now I'm back to delta 0 or L nut if I removed all the force, right? So this is L nut again. And that is because it's elastic. So the jump from here to here to here, that means it's elastic. I removed this force and it restores its initial length. That is elasticity. And that is a concept that you see a lot in engineering when it comes to the elastic modulus of some materials. So it's very important that you really understand this graph and what it really means in the physical world, because so many materials are actually linear elastic, and that is one reason why we talk about this topic today. But we can talk more a little bit about springs here, and we can define springs properly. We need to add one last state here to have the complete picture. So let me extend the line here. So let's say we have another state, which is my state number 5. And now I'm actually applying a force in the opposite direction, so that now I have a force of, let's say, 1 Newton here. And now, of course, I compressed my spring. And so my L naught would still be the original length, L naught, but now I have a negative delta L, which would be this here. And so this is negative delta L, and let's call that 5. And because the spring is linear elastic, if that is 1 Newton, then this stretch delta L1 would be equal to the negative delta L5. So they stretch in the same direction. And that is really the definition of a linear elastic spring. Just for comparison, let me go back up here and let me show you what would happen if you would have a nonlinear elastic spring. So I'm going to draw this graph again. And that is something we don't deal with in this class, but I want you to understand this. So let's say you have a regular material, let's say steel, for example. Steel is initially elastic, you can pull on it and it goes back to its original length and so on. But once you go beyond a certain delta L, like once you put a lot force on it so that it stretches too much, so you can also say that you have a delta force on there. So once you have too much force on there, you go beyond this point, then the material actually starts to become plastic and it really looks like this. Again, this is beyond the purpose of this course, but now if you remove the force, the material would actually go back to this stage. And that is something that we have all experienced before. So actually both of them, we have experienced this and this. If you take, for example, the pen and you open it up that you're using right now, there's usually a spring inside. And you can pull on it and it goes back to its original length. But once you pull too much on it, and I encourage you to do that, just find a cheap pen in your home and pull on it and pull so hard that it does not go back to its initial length. So you will actually find a behavior that is similar to this one. And that is really what is the plastic region. So again, not the topic of this course, but it's always good to know. So this is plastic. Whereas this part here is the elastic region. So that is pretty much the difference. And of course, in this class, we only deal with materials that act in this region. And this is for classes like strengths of materials and other things. We do not worry about this here. But it is important for us to understand the difference so that we can now move on to the definition that engineers use for these springs. And the first thing we need to understand is that everything that stretches a spring is considered positive. And that's easy to remember, right? So if you add some weight to it, you add length to it, and therefore you use the positive sign. So a stretched spring, is positive. And on the contrary, of course, a contracted spring is negative. So engineers automatically know when they see a positive or a negative what is acting or what is happening in the spring. So is it stretched, is it extended, or is it contracted? Like here, for example. So please keep that in mind. In fact, let's say that this is positive, this is negative. So here I have a negative, but here I have a positive, here I have a positive, and here I have a positive. That is how engineers define that. And I think now we have a solid understanding of that. Of course, we need to talk about something that you already talked about in your physics class, and that is the spring constant. And we all remember like one formula or the other, which comes from Hooke's law. By the way, Hooke's law is visualized here effectively, but Hooke's law really says that the force is proportional to the extension of the spring. So force in spring is proportional to the extension in spring. Let's highlight that. That is fairly important. because that is Hooke's law. And again, you probably already knew this from your physics class. There's no question about it. But again, we all want to be on the same page and want to have a solid understanding of the concepts that we're using in this class. So how is this formulated? And that is something you have, of course, worked with as well before. You have seen the formula in one way or the other, but let's say the force in the spring is usually equal to what is called K times, and I think in physics most students use X, but here in this class we're using S. And so this is really the spring constant. Whereas this is the stretch. And so now you of course know that this here is the force in spring. So now if you understand the relationship and the picture that we just drew above, then you will never struggle with any formulas or with any units here. In fact, look at this, right? So you know the stretch. The stretch we know is always given in what? In like a distance. Let's make it in the SI system. So let's say it's in meters. And the force in the SI system is always given in, let's say, Newton. So now you may ask yourself, what is the spring constant? And the spring constant, of course, has to complement this. So how do I get from meter to Newton? By something called Newton per meter, right? So here I need Newton per meter. And that is really how that is defined. So the real formula then reads F in Newton is equal to K in Newton per meter multiplied by S in meters. And likewise, you often need to find actually the stretch rather than the force in the spring. So when that is the case, then you have to find the stretch in meters. And that, of course, is just rearranging of this formula, the force in Newton divided by K, the spring constant in Newton per meter. So that, once again, is an important formula. So let's highlight it. This is what you need to memorize to solve the upcoming problems and therefore the problems on your homework and, of course, quizzes and exams. So please memorize this. Of course, you know this. What's important to me here is actually the physical understanding and how I derived the K value. So I know I have a spring, I know I have a stretch, and what is the unit? Because in my experience, students often forget the unit of the spring constant, and you can really derive this from Hooke's law and the definition of all the other two components, the stretch and the force. So we understand how that is defined. Let's highlight our spring constant here so that we don't forget that K is actually the spring constant. And because K is so important for our upcoming problems, let's write down one last thing. So that relates to the spring constant. Let's say you have a 100 Newton per meter spring constant K. So the question is, what does that mean physically? So please understand that if you have a spring that, let's say, initially looks like this, and then you apply 100 Newton to it. So let's say here I now have 100 Newton. Then I have a delta L of 1 meter. So in other words, what this means is that 100 newtons are necessary to stretch the spring 1 meter. So this would be a very weak spring. It would be very useless in construction or for structural engineers, but the concept applies, right? So whatever number you have, that's how much it takes to stretch it by 1 meter. And that is the real physical interpretation of the spring constant. So in real life, you will find more something like a meganewton per meter or something like that, or even larger numbers. So that then would take 1 meganewton to stretch the spring by 1 meter. But this is how you read the spring constant. And that is important to understand for engineers. Often in the classroom at this point, I ask the students to go ahead and Google the spring constant of a general sports car. so that they can calculate how much the car displaces downward if a student steps into the car. So maybe go ahead and measure your own weight and then assume a sports car spring constant. You can find that on Google. And then step into the car virtually and tell me how much the car displays downwards, right? So if I were to draw this down here, so let's say I have a car that is somewhat like that. Again, my fantastic artist skills here, but here I have a car and I know a spring constant. So there's a spring constant K, sports car. And then there is, of course, a student. So here's F student. And you can just use your own weight for this. And this you can Google. And then ask yourself, hey, what happens if the student steps into the car? And how much does the car displace? Because once the student is in the car, then you probably end up with the entire frame a little bit lower. So that would look something like this, right? And so my question to the student then is, hey, what is this delta L is usually what we call it. And so the question is, what is that value in, let's say, meters or in foot? Either one would work. And please understand that this is a car and not a unicycle. And that's all I can tell you at this point. So please be careful. Don't fall into any traps here when you solve problems like that. But you are an engineering student, so of course you got this. So let's take a look at this entire page here now. That concludes our understanding of springs. We definitely understand what linearity is now and what a linear elastic spring is. So it goes back here. We applied this to Hooke's law, and we even derived the spring constant. By the way, K stands for Konstante, which is a German word because Hooke spoke German. So therefore it's the spring constant K that defines the displacement of a spring. However, I believe we are now ready to tackle problems with springs in them. And of course, we will now apply this concept and specifically this formula to our cable structures so that we can calculate the extension or the stretch of those springs. Of course, I didn't show you how to do that here in theory, but this is easier to be shown in a practical problem. So let's move on to our example problems.